going to remind ourselves what linear regression is by starting out from a model that just represents the average and then adding an x variable to move to linear regression. So you might ask yourself, for example, how expensive are houses in my city on average? So we can compute that average. As statisticians, we like to model this. And the model that corresponds to the average would be just y equals mu, the average, plus epsilon, the error or the residual. And because it is a model, we have to specify a distribution for the residual. And this is a Gaussian distribution here with the standard deviation of sigma. Now, we are almost always assuming independence here between the observations to estimate the parameters. Y is the random variable for house price in this example. Mu is the expected value, which will turn out to be the average. And epsilon is just the difference between the expected value and the actual house price, the individual house price. This basic average estimator is not that useful often, right? So if you're buying a house, you might be more interested in the question, how expensive is a house of a given size, a certain size? And then you have to decide, well, what do I mean by size? And one thing you might choose as a variable is square footage, the square footage of the house. So how expensive is the house with a certain square footage on average? So I'm still have on average in here, because even if you take a house of a certain size, say 1,500 square feet, all those houses are not going to be exactly the same value. They're going to average around some value. And so we still use the word average, and that means we still have an error in there. The average corresponds to the expectation mathematically, right? So there's a different expectation for each house size. If we want to build this into the model, we just specify mu and elaborate here. And rather than just having a mean, which corresponds to the alpha here, we allow for a linear change as a function of x, where x would correspond to square footage of the house here. Plugging that back into the equation, we have y equals alpha plus beta x plus epsilon, a linear regression model with one variable. Nothing has changed on the epsilon, same thing as before. We are specifying a linear relationship here, and that is an assumption. The assumption may be appropriate or not, right? The data are right. We are trying to approximate the data. This is a linear approximation that may or may not be right. But we have to do something. The assumption of independence is always required, because otherwise we get into trouble with estimation. That's an advanced topic. Okay. So these parameters have names. Alpha is the intercept, or sometimes called constant. Beta is the slope. And alpha can also be interpreted as the expected value in case x equals 0, right? Because the expectation of epsilon is 0 as specified there. And then for any given value of x, we can compute the expected value. And it's alpha plus beta xi, and then the expected value of epsilon is 0. So that's why this is that. So for every different square footage, we get a different expectation. We no longer have a single expectation. We have a whole bunch of them, and they form a line. How many parameters do we have here? We have 3, alpha, beta, and let's not forget about sigma, which parameterizes here the variance structure. Alpha and beta are for the mean structure, and sigma for the variance structure. That's it for this segment.